So yeah, my name is Hannah and I'm chairing the Biostatistics session. We have 5 talks coming up and we're starting with Abdul, who is joining us online. Abdul will be presenting his work on continuum of maternal healthcare services in low and middle income countries, a multi-level analysis.
Thank you, Hannah. Can you hear me and can you see my slides?
Yep, we can.
Okay, thank you. Hi, I am Abdul Baten. I'm a PhD student at the Swinburne University of Technology. This is the part of my PhD study, and the title of my study is Continuum of Maternal Healthcare Services in Low and Middle Income Countries, a multi-level analysis. These are the outlines of this study. Maternal mortality is a significant global public health challenge, and it remains unacceptably high in low and middle income countries, though maternal death declined 34% between 2020 to 2020. Worldwide in 2020, nearly 1 maternal death occurred in every 2 minutes. That is daily estimated 800 maternal deaths. And almost 95% of all maternal death occurred in low and middle income countries, especially sub-Saharan Africa and South Asian region. Research indicates that effective utilization of maternal healthcare services can reduce the maternal mortality and morbidity rates. And it also found that maintaining continuity or continuum of care may reduce the risk of combined neonatal, perinatal, and maternal mortality by 15%. The continuum of maternal healthcare service is a systematic approach that starts with high-quality antenatal care, followed by skilled birth attendant and postnatal care. It was found that maternal healthcare service utilization can significantly decline from the antenatal to postnatal period within the continuum of maternal healthcare. So to understand the factor causing gaps in antenatal to postnatal care is crucial for the seamless maternal and newborn healthcare service and improving health outcomes and women well-being. Therefore, the aim of this study is to estimate the prevalence and visualize the country-wise differences of the continuum of MHS utilization in LMICS, and to investigate its determinants using 2-level hierarchical models, considering both individual and country-level factors. Methods, data source. For this study, we utilized the latest standardized cross-sectional demographic and health surveys between 2015 and 2022 from 35 LMICs. Study variable. For this study, we considered the outcome variable as the continuum of MHS utilization at the antepartum, interpartum, and postpartum stages. And the outcome variables are dichotomous, which are generated from the 3 indicators of maternal health care, and that are the at least 4 antenatal care visit by the skilled provider or NC4 plus SP, skilled birth attendant or SBA, and postnatal care or PNC. Explanatory variable. For this study, demographic and socioeconomic variables based on Anderson behavior models of healthcare services were considered as explanatory variable. The Anderson behavior model is a systematic analytical approach that uses the factors that influence the health care. That model comprised the external environmental factors along with 3 dimensions of population characteristics. These include predisposing factor, enabling factor, and need factors. For this study, we started with the estimate of the prevalence of continuum of maternal healthcare service and made them visualize the country-wise difference. Secondly, distribution between the socio-demographic factors and continuum of maternal healthcare service utilization was assessed. Finally, 2-level hierarchical models were used to determine individual level predictors while controlling the effect of country level predictors. The results were presented based on odds ratio with 95% confidence interval. In this bar diagram, present the full prevalence of the individual maternal healthcare service as well as the continuum of maternal healthcare service, and it was found that at least 4 antenatal care visit prevalence was around 56%, Skilled birth attendants were found 71%, and the postnatal care is around 54% for the selected LMICs. On the other hand, in case of continuum of maternal health care service, at the antepartum stages, the prevalence was 55.8%, but it reduces to the 36.7% in the postpartum stages. In this map, we present the country-wise prevalence of the continuum of MHS at the antepartum stages. And the average prevalence was found 55.8% for the selected 35 LMICs. The lowest prevalence was observed in Afghanistan, and it was found only 16%. The highest prevalence was found in Indonesia, and it was around 89%. In the second map, we present the prevalence of the continuum of MHS at the interpartum stages, and the average prevalence was found 47% for the selected LMICs. The lowest prevalence was observed in Afghanistan, and the highest prevalence was observed in Indonesia. In the final map, we present the continuum of prevalence of continuum of MHS for the 35 LMICs for the postpartum stages, and it was found the lowest prevalence was found in Afghanistan, and the highest prevalence was found in Indonesia. Here present some results of the distribution of socio-economic characteristics of women across the continuum of maternal health care service. Our full sample size comprised of about 246,000 of women for the selected 35 LMICs. And among women who continued maternal health care services at pre, inter, and postpartum stages, on average 68.4% of women over 25 years old. An average 60% of women who did not continue the maternal health care service lived in rural areas. Here present some descriptive results of the level 2 factors, that is the country level factors. And it was found that the women literacy rate was about 62%, ranging from 22% to 97% for the selected LMICs. The average health provider to population ratio was 14 per 10,000 people for the selected LMICs. In case of model, first of all, we run the null random intercept model to find out the ICC value to see the data eligibility. And we found that the first null model, the value was ICC value was found 0.18. For the second null model, it was also 0.18, and the null model 3 for the postpartum stage, it was 0.19. After that, we utilized the multi-level analysis since we found that all of the null models ICC value greater than 5%. Here, first of all, we run the multi-level model for the individual indicators of maternal health care to see the relationship between them. And we found that women who received at least 4 antenatal care visits by a skilled provider, 2.8 times more likely to utilize a skilled birth attendant. And women who utilized at least 4 antenatal care visits and skilled birth attendant were 1.6 and 19.2 times more likely to respectively utilize postnatal care compared to their counterparts. Finally, we run the full model for the continuum of maternal health care services from antepartum to postpartum stages, considering both individual level factors and country level factors. And it was, first of all, we present the fixed effect result, and it was found that women whose age is 25 years or more, who are educated, who are from higher wealth index group, who perceived that distance to health facility was not a big problem, and who have a media exposure, whose age at first birth were 18 years or more, who are employed, and who have a decision-making power in the family, were more likely to utilize the continuum of MHS compared to their reference group. For the country level factors, we found that ratio to health provider to population showed significant positive association with the continuum of maternal health care services. On the other hand, women who resided in the rural areas whose fertility is 2 or higher were less likely to utilize the continuum of maternal health care service. Here I present some results of the random effects. We found then substantial variability in the loggers of continuum of maternal health care service utilization at the antepartum to postpartum stages due to the difference between the countries. The ICC value for the full model 1, 2, 3 were respectively 0.13, 0.14, and 0.15. That means that approximately 13, 14, and 15% of the variability in the utilization of continuum of maternal health services due to the difference between the countries. In conclusion, we found that the maternal health care service utilization decreases from antepartum to postpartum stages. To address this, policy should focus on the engaging pregnant women early in the maternal health care and improve the quality of antenatal care for enhancing subsequent maternal health care service, addressing the disparities in the utilization of maternal health care service in LMICs requires equitable facility distribution and economic levels. A multi-sectoral approach integrating health and non-health initiative, particularly for socioeconomically disadvantaged women, including who are less educated or not educated, who are from lowest wealth index group, and who are from the rural area, should give an impetus to them to enhance the maternal health care service ability, accessibility, and completion rate, aiming to meet the related sustainable development goal by 2030. These are the selected references. Finally, I would like to thank all audiences and my co-authors. I also acknowledge my scholarship sponsor and Soinban University of Technology. I'm grateful to the ECSSC 2024 for giving me opportunity to present here. Thank you.
All right, thank you, Abdul. Next up, we have Jinghong, who will be presenting their work on interpret the estimate framework from a causal inference perspective.
Okay, I'll start share my screen. So Hannah, can you see my screen?
Yes, we can.
Oh, okay. So, okay, that's fine. Hello everyone, my name is Jinghong Zheng. I'm a statistical programmer. Today my topic is interpreting the estimate framework from causal inference perspective. We will go through 3 sections. First, we will look at some industrial guidelines and estimate framework. Then we will look at a causal inference framework and use it to interpret intercurrent events in the estimate framework. ECSSC E9 is a guideline for statistical analysis of clinical trials in the pharmaceutical industry. It proposes considerations for many different trial aspects, such as trial design, data analysis, and trial monitoring. After the ECSSC E9 guideline, ECSSC E9 R1 guideline is proposed. This new guideline provides clarification and updates on the previous statistical guideline. This new guideline focuses on statistical principles related to estimates and sensitivity analysis. It also proposes the estimate framework. The estimate framework explains what is a treatment effect in a clinical question. The treatment effect is represented by the definition of an estimate. An estimate has 5 attributes. They are target population, treatment, endpoint, population level summary such as odds ratio or relative risk, and intercurrent events. Today we will focus on intercurrent events. Intercurrent events are events that occur after treatment initiation and may affect interpretation of the treatment effect. For example, it is quite common in clinical trials that some participants stop the study treatment and quit study, or they may take some concomitant therapies in addition to study treatment. These intercurrent events change the ideal situation that we want a clinical trial to be. ECSSC E9 R1 guideline proposes 5 strategies to analyze intercurrent events. There are treatment policy strategy, hypothetical strategy, composite variable strategy, wide-on treatment strategy, and principal stratum strategy. For each strategy, we will look at a simple example to understand. So in this case, some participants use concomitant therapies in addition to study treatment. And so the intercurrent event is use of concomitant therapies, and we assume that concomitant therapies are allowed. So the treatment policy strategy will include use of concomitant therapies in the treatment definition. For example, instead of the effect of study treatment, we may estimate the effect of study treatment plus concomitant therapies. For the same intercurrent event, the hypothetical strategy will make endpoints after use of concomitant therapies missing. So, for example, we may make endpoints at the first and second assessment missing, and then we use some statistical methods to impute those missing endpoints. In this case, some participants die between the first and the second assessment. So the intercurrent event is death here. We assume that the endpoint is a disability index and it does not consider death. Then the composite variable strategy will include death in the endpoint definition. For example, we may define death as the worst disability category. Still, for the same intercurrent event, the while-on treatment strategy will use available endpoint data before death. So, for example, we will use endpoint at the first assessment to do data analysis. In this case, some participants discontinue treatment due to treatment toxicity and withdraw from study. So the intercurrent event here is treatment discontinuation. And for this participant, they do not have available endpoint assessment. The principal strata strategy will first identify a subpopulation of participants who would or would not experience intercurrent events, and we will then estimate the treatment effect in this subpopulation. For example, instead of the target population, we may interested only in the subpopulation who would tolerate treatment toxicity. So these 5 strategies are mainly explained as text in the ICH E9R1 guideline. So actually, there are underlying theories closely related to causal inference. To help us understand this 5 strategy in the more statistical way, we will first look at what is a causal inference framework. The basic idea in a causal inference framework is potential outcomes. So we assume the simplest situation where there is only treatment, endpoint, and randomization with no confounders. So for one participant, there are 2 potential outcomes. If the participant was randomized to the treatment arm, this participant would take the experiment treatment and have an associated endpoint. On the other hand, if this participant was randomized to the control arm, this participant would take the control treatment and have an associated endpoint. So before the actual randomization occurs, these 2 potential outcomes are possible. For this participant, the individual treatment effect is a difference between 2 potential endpoints. And for all participants involved in a clinical trial, the average treatment effect is expectation of all the individual treatment effect. The average treatment effect is one kind of estimate, and the formula for the average treatment effect here will be used to interpret intercurrent events and associated 5 strategies. So for the treatment policy strategy, from the formula just presented, the meaning of variable X changes from study treatment to study treatment plus concomitant therapies. And for the hypothetical strategies, the observations of variable Y will now have more missing values that some of which are manually created. And for the composite variable strategy, the meaning of variable Y changes from index with no depth to index with depth. And for the while-on treatment strategies, the meaning of variable Y changes from endpoints at second assessment to endpoints at first or second assessment. For the principal stratum strategy, we first have to identify a subpopulation that we want to estimate the treatment effect for. So for example, suppose we are interested in the first subpopulation who would tolerate both the experimental and control treatment, and we want to estimate the cost treatment effect in this subpopulation. So now the formula for the average treatment effect becomes an expectation of all the individual treatment effects conditional on this subpopulation. The principal stratum strategy actually also requires certain assumptions to build statistical models. So causal inference methods can help us interpret different components in estimate framework. And with these methods, actually, it is possible to it is possible that more strategies can be proposed. For example, if we have an intercurrent event that is use of one concomitant medication, and this medication can interact with the experimental treatment and can also affect the endpoint. So now the intercurrent event actually becomes a confounder. So for a causal model, we can adjust for these confounders in our analysis. Through this example, I would like to encourage further development on the estimate framework. So that's me. Thanks for listening.
All right, thank you, Jinghong. Next up, we have Kylie, who's also joining us online. Kylie will be presenting their work on sample size calculations for partially clustered clinical trials.
Thanks, Hannah. So this is work, part of my PhD research that's being conducted at the University of Adelaide and the South Australian Health and Medical Research Institute with additional funding from the AusTRIM Research Network. Sorry, it's just broken on me. Let me just, you're not seeing my slides there, are you?
Not at the moment, but we
No.
will.
Okay, let's try that again. It just dropped out. All right.
Yep, we can see.
Okay. So my work's motivated by the statistical challenges that occur when working on trials in neonatology. So here the outcomes are measured on infants and can include singletons and infants from multiple births. The intervention may be administered during pregnancy, like a nutritional supplement to the mother, or to the individual infants after birth. And working on these trials raised the question of how to deal with the clusters of size 2 or 3 that result from multiple births when calculating the required sample size for these trials. So these trials are an example of partially clustered trials. It's often assumed when we're talking about clustered data that all individuals or observations belong to a cluster. For example, when we're talking about cluster randomised trials. However, many trials involve partially clustered data where only some individuals belong to a cluster. And so our data consists of a mixture of clustered observations and independent observations. These partially clustered trials occur in many applied areas, and examples include trials of group-based treatments versus an ungrouped control, trials that allow the inclusion of family members like infants from multiple births, trials that allow the inclusion of multiple body sites per individuals like eyes or joints, and trials that use a re-randomisation design where participants may enrol in the study one or more times. My PhD work defined 4 different types of partially clustered designs, and these are defined by whether the clusters exist before randomisation, like infants from a pregnancy or multiple body parts of a person, or the clusters may be induced only after participants have been randomised, for example, by assigning people in the same randomised arm to education classes. And my interest is in the 3 designs for pre-existing clusters, which differ based on the randomisation methods that's used for the clustered observations. So this randomisation may be of the individuals, it may be at the cluster level, or balanced randomisation can be used to assign, for example, one member of each cluster of size 2 to alternate treatments. So trials with these designs are relatively common, yet compared to designs with post-randomisation clustering, they've received limited attention in the methodological literature. So what is known about how to design these trials? Well, we know that if the clustering is not accounted for when calculating the required sample size, then the trial may be over or underpowered. However, limited methods are available for partially clustered designs. Sample size methods have been developed for the case of clusters of size 2 based on generalised estimating equation models that account for the clustering with robust standard errors and either an independence or exchangeable working correlation structure for the clustered observations. However, no methods have been developed for partially clustered trials with larger cluster sizes, which occur across fields like neonatology, orthopaedics, dermatology, and in trials that use a re-randomisation design. So the aim of my research was to extend existing sample size methods to settings with larger cluster sizes, to validate the newly derived methods in a simulation study, and finally develop an online sample size calculator that can be used to calculate the target sample sizes for partially clustered trials with any distribution of cluster sizes. So how can we calculate the required sample size when there will be clustering? Well, an approach used for other clustered settings is by using design effects. So the process here is to calculate the required sample size assuming independence using a standard sample size calculation like for a t-test, and then to multiply this by an appropriate design effect. So design effects are calculated as the ratio of the variance of the treatment effect from treatment effect estimate from a clustered model to the variance of the treatment effect estimate from a model that assumes independence. And when this design effect is greater than 1, then the clustered design requires a larger sample size to achieve the same power as a trial consisting of only independent observations. And if it's less than 1, then the required sample size is decreased relative to that independent design. So deriving the design effects was done algebraically for a linear model for continuous outcomes and both logistic and log binomial models for binary outcomes. The variance of the treatment effect under clustering for the numerator of the design effect was taken from a GEE with either an independence or exchangeable working correlation structure. And the denominator was the variance under independence from a standard linear, logistic or log binomial regression. Design effects for each of these 3 outcome models were derived for both cluster and individual randomization. And while balanced randomization had also been considered for clusters of size 2, it's not commonly used and is more complex to extend to larger cluster sizes, so we haven't considered that further here. So the algebraic work involved deriving the required terms for a cluster of arbitrary size k, including for the independent observations, which were treated as clusters of size 1. Summing these over all clusters to get the variance of the treatment effects, and then after quite a few pages of algebra, we've derived the final design effects. So the resulting design effects for a continuous outcome are shown here. So the design effects depend on the method of randomization for the clustered observations, the intra-cluster correlation coefficient, which is the strength of the correlation between outcomes from the same cluster, the possible cluster sizes, K, which range from 1 for the independent observations to capital K for the maximum cluster size, and the proportion of observations that belong to clusters of each size, denoted by the gamma K terms. So to visualise what these formulas look like, this figure plots the design effects for scenarios with clusters up to size 4 in the proportions that we might expect in a trial in preterm infants. So 70% of the clusters here are of size 1. The x-axis varies the ICC from 0 to 1, and it should be noted that in many partially clustered trial settings, the ICCs can be quite high. The dashed lines are design effects for when the cluster randomization is used, and as in cluster randomized trials, the design effects here are greater than 1, meaning that the sample size has to be inflated compared to an independence design to account for the clustering. And the solid lines are design effects for when individual randomization is used and result in a value of less than or equal to 1, meaning that the target sample size is less than or equal to a design with all independent observations. For a binary model using the logit link, the design effects for cluster randomization are the same as for continuous outcomes. The formulas for individual randomization are more complex and additionally depend on the link function and the prevalence of the outcome in each group. When the log link is used, the terms involving the prevalence estimates in red differ, but the rest of the formula structures are the same. And in the validation study, we were able to confirm the accuracy of all of these design effects in a number of real-world settings. So to illustrate how these design effects are used, we'll consider a hypothetical trial to assess the effect of a new infant formula on growth amongst infants born preterm. So infants will be randomised to either a standard formula or a new formula, and the primary outcome is the standardised weight at 18 months measured by a Z-score. And a clinically important effect here would be to increase this by 0.3 units compared to the standard group. So I developed an R-Shiny sample size app that uses my design effect formulas to calculate the required sample size for trials like this that include partial clustering. So here's what the app looks like for our example. The outcome in our case, weight Z-score, is continuous. We then need to enter in the sample size required to detect the effect size of interest if we assume that all observations will be independent. So that might be done using a standard sample size calculation, say for a 2-sample t-test. And here we put in the result of that calculation, 235 infants per group, to detect the difference of 0.3 at 90% power. Next, we need an estimate of the ICC, perhaps from previous studies, for weight at 18 months. And so we use 0.58. And we then specified the working correlation structure for the GEE that we're going to be use in our analysis. For the randomisation method, we do know that parents of multiples often prefer that their infants receive the same treatment. So in this case, we'll consider cluster randomisation and assign infants from multiple births to the same treatment group. In the next section of the app, we enter in details of the clustering. So if it's expected that our population will include twins and triplets, then the maximum cluster size is 3. And it's estimated that 70% of the infants included in the trial will be from a singleton pregnancy, 25% will be twins, and 5% triplets. So those values are entered as the percentage of observations. Alternatively, the app does allow you to enter in the percentage of clusters if instead you had estimates of the percentage of women, say, who would be pregnant with each order of pregnancy. So based on those inputs, the app selects the appropriate design effect formula, calculates its value, and multiplies it by the independent sample size to return the required number of infants and mothers that are needed for the trial to appropriately account for the clustering due to the multiple births. So in this example, we can see that 283 infants per group are needed, which given the estimated proportion of clustering can be achieved by consenting 239 parents per group. So the target sample size is greater than if only singleton infants were included, but the results may be more generalisable to a wider population. So in summary, the aim of this project was to develop and validate these new sample size formulas for partially clustered trials that can be used for trials with varying cluster sizes, and we've implemented that in a sample size calculator. Then by making these tools hopefully easy to use and freely accessible and with published guidance to sit alongside them, the aim is to ensure that these sample size methods are accessible to both health researchers and applied statisticians and can be used to hopefully improve the quality of these trials. So the app is in the final stages of testing and will be live soon, but if anyone's interested in this or working in a related area, I'm happy to share that, and please do get in touch. Thank you.
Great, thank you, Kylie. Our next speaker is Michelle. Michelle is joining us from Christchurch and will be presenting on species distribution models for projecting impacts of climate change and implications of implications of management for a data poor coastal species, barred surf perch.
Am I unmuted? Yep. Okay. Yeah. Keep. All right. Thank you. I just wanted to start by acknowledging all of my co-authors. Science doesn't happen in a vacuum, so these are their lovely smiling faces. This project is a piece of a large collaboration between University of California, Santa Barbara and Point Blue Conservation Center, or Conservation Science. Today, I'm going to tell you a story about sandy beaches. Sandy beaches and surf zone ecosystems cover 31% of ice-free coastline worldwide. And in some areas, they can cover a lot more, like southern Santa Barbara County, where some of this data comes from. They make up to 75% of the coastline. And surf zones are the area of whitewater you can see in this aerial photo. And these sandy benthos are iconic cultural assets. They can be really important for tourism and recreation. They can support coastal economies and some fisheries. While they're iconic and often considered for tourism, they are rarely considered for study and conservation management. But these ecosystems have a number of functions and services. They buffer and absorb wave energy, accumulate and store sand, cycle nutrients, and are part of a rich secondary productivity food web. Beaches are affected by climate change in a number of ways, mostly through sea level rise. And while beaches themselves can move and adapt to climate change in a way, that depends on the landward boundary of the beach itself. So development, armoring, and bluff back beaches will limit the area that a beach can move inland, subsequently altering the habitat. And this can result in changes in species and even loss of species as we lose that upper dry back beach. One strategy to mitigate for climate change in California is a network of marine protected areas. Marine protected areas provide a spatial area where fishing and harvesting is not allowed. And the idea is it gives the species time to recover from stressors, but it also may allow them time to adapt to climate change, changing temperatures and things without the pressure of fisheries. California established a large network of MPAs, completed in 2012. And as part of the review of those MPAs, we've been looking at the data and trying to understand other drivers of the species. So today I'm going to talk about our current project, which looks at mapping habitat and species distributions in California, stealing some of that MPA data. So we're trying to map sandy beaches in California across the whole coast, compare that with observations from long-term monitoring through species distribution models, and estimate the current distribution of species. We then aim to repeat this for future climate scenarios and predict where species and habitat will be, and see if the MPA network of today can predict the ranges of the species in the future. So today I'm going to talk about one of our focal species. This is barred surf perch. It's a small perch shaped, it's about this big. It's an important recreational fish. In this graph, we can see a comparison of recreational and commercial landings for a couple of different surf perch. This dashed line at the top is barred surf perch recreation landing, so actual just sport fishermen on the beach catching them, compared to this is the recreational landings of a sister species, red-tailed, and then the commercial landings are way down at the bottom. Very few commercial landings, mostly it's a recreational species. They're very abundant in California surf zones. They're harvested at all sizes. There's no size limit on what you can harvest. I don't believe there's a bag limit either, which means you can harvest as many as you want. They have very small home range sizes. Tagging studies show us that these are less than 3 kilometers. They also bear live young, making them possibly susceptible to climate change because they cannot adjust their range quickly. We also know from previous studies that they do respond to MPAs. So a lot of this data comes from a long-term monitoring project where we sample the sandy beach using a seine. That's this picture here. Big net, you open it up in the ocean and pull it into shore, capture all the fish, identify and measure them. And then this figure shows the abundance of those species over our different years. We sample 3 times a year at 26 different sites. They're arranged here from north to south across the x-axis, and they're paired with red being the marine protected area and blue being the reference site. And we can see that in the north, there's no catch of barred surf perch. This is beyond the natural range that they currently inhabit, so we don't observe any up there. There's this peak in the middle of the range in central and the upper part of Southern California, where we have high abundance, and then it trails off as we go further south. So we see a regional change in their distribution as well as some site-specific peaks in abundance. This is a map of our study sites along the California coast. You can see that there are some gaps in our sampling protocol. This is because some of these areas are rocky shore, meaning there's no sandy benthos. Some of these areas are very, very difficult to access. There's no roads, there's no way down the cliffs. They're very tough. So we know that there is a regional difference as well as site-specific differences. So we're interested in what is driving these. But because we have some gaps in our study area, we've decided to include some citizen science observations from iNaturalist, taking advantage of integrated species distribution models. These fish are charismatic, easily identified, so there's a number of observations that are deemed trustworthy on iNaturalist. So we can add those to our model and combine the likelihood. I'm just using INLA, integrated nested Laplace approximation, in the R package. I'm not making any crazy assumptions here. Slightly regularizing priors in the spatial field. The hardest part is developing the mesh, the shared spatial mesh, which can influence your predictions. So I quickly ran it with two covariates. On the left-hand side is our observations, the sites where we sampled, as well as the iNaturalist observations. And on the right is just the current distribution according to the two covariates in my model. And this is the mean probability of abundance. It's nice when the model shows you what you already put in it, so I know it's doing something. What's interesting is up at the North Coast, we do have some high probability, which seems suspect to me, but it might be due to the few covariates, or perhaps, according to the environment, those species could live there, but something else is blocking their current range. So next is to project this to future climates, explore a possible temporal model, different mesh parameterizations, and different covariates, including habitat. We're partnering with the US Geological Society to get estimates of beach width, beach slope, and erosion due to sea level rise, as well as wave height for the entire coast of California. And hopefully these will help us assist managers in answering some questions about how to protect future ranges and whether or not this system of MPAs can be used to allow species to adapt to climate change. And with that, I'll acknowledge my funders and the land access, as well as Massey University for the funding to attend this conference. Thank you.
All right. Thank you, Michelle. Our final speaker is Hannah, joining us from Perth. Nice name, by the way. Hannah will be presenting their work on estimating tumor registry catchment area residency for the adjustment of solid cancer incident in atomic bomb survivors. We can't hear you. Test. Yep. Hello.
Excellent. Okay. I was just celebrating / lamenting that I get the coveted last delegate position talk. So my name is also Hannah. And today I will be talking about one of the projects I've worked on heavily in the last year at the Radiation Effects Research Foundation in Hiroshima, Japan. And at RARF, we study the health effects of radiation exposure from the atomic bombs on the survivors and their offspring. So by way of introduction to the research and to RARF a little bit more, I thought I would share about our three major population cohorts that we study. So the atomic bombs were used in 1945. So we have a single time point of exposure of large amounts of radiation. And sort of against all odds, as soon as 6 weeks after the bombings, Japanese and American scientists were already working together. And that served as the really early origin points of what is the present day RARF. So in 1950, due in large part to a national Japanese census, the researchers were able to organize a really robust cohort of about 120,000 survivors across the two cities. And they entered follow-up for mortality and cause of death. And that is what we call that our lifespan study, and that is still ongoing today. In 1958, the Hiroshima and Nagasaki cancer registry systems were formed, so we also began follow-up for cancer incidents. And in that same year, a subsample of the LSS was put together in order to have sort of a forum to gather much more detailed clinical information. So these individuals still to this day come into RARF for clinical visits every 2 years. I think we have like well over 4 million biosamples from these individuals, and they do other things like fill out questionnaires and participate in some smaller scale studies as well. So today's presentation will focus on that cancer incidence data from the LSS and also some of the AHS data. And in addition to that, the two other population cohorts that we study are a smaller group of individuals that were exposed to radiation in utero, and we also study the F1 offspring cohort. So as I mentioned, in 1958, Hiroshima and Nagasaki established cancer registry systems. And as those are very region-specific cancer registry systems, they are formed relative to a specific catchment area. So from RARF's perspective, when we're interested in cancer incidence, we are using data linkage and going through a lot of paperwork to be able to identify our LSS individuals who have developed cancer. However, the challenge in this is that given that it's not a national cancer registry system, one thing we have to think about is that all of our individuals in the LSS would have started within the catchment areas, but over time they may leave the catchment area. And if they develop a cancer outside of the catchment area, we will not be able to retrieve that through data linkage, and that can result in underestimates of cancer incidence. So I'm going to talk to you about the migration aspect, but sort of the big picture of this project is to look at cancer incidence of our LSS cohort, which we've done multiple times before, but as time goes on, we're also extending our follow-up time. So this latest analysis will extend follow-up time for another 10 years up to 2019. So with that, we also have to upgrade our migration data for another 10 years. But migration is actually not something that we explicitly ask about or track in the LSS population. So what we've done is made use of that AHS subcohort, which is far more rich in data. We have address information from their clinical visits, information from mail surveys, a whole breadth of sources. And even then, it's not explicitly asking about migration. So we kind of end up with this sort of proxy migration data, which is subject to biases and lots of processing and missing data challenges. So I think that actually was the most challenging aspect of the project, but we'll focus on results and colorful graphs that are more exciting. So let's assume I did a good job cleaning and processing the data, and then I'm interested to start answering questions about migration. So what I'm interested in specifically is the hazard of leaving the catchment area. And we also allow for people to return back to the catchment area. So I'm also concerned about the hazard at any point in time of someone coming back to the catchment area. So the data is processed as time to event data, where we consider those two migration events, or subjects can also be censored in the data set. And there are, of course, many ways to go about estimating hazard functions. And the approach that we've taken in the past and continued to use, which is sort of re-represent the data in terms of person-year tables, and then we can employ an approximate Poisson regression to the data, rather than doing something like Cox regression, which may be subject to some constraints or more stringent data assumptions. So just a little bit of detail on what those person-year tables might look like. This is a little snapshot. So we've partitioned the time covariates into groupings of calendar year, attained age, age at exposure, city, and sex. We would then have the accumulated person years, the number of individuals that were at risk in that covariate partition. And then we also have person year weighted averages of our time variables. So for estimation, again, we're going to use Poisson regression and model the number of events as a function of our covariates. We're just going to use 2 time dimensions. On a continuous scale, the 3 time dimensions are perfectly correlated, so often we can leave one out. And despite the fact that we've categorized the data, I decided to apply a tensor product spline on our 2 time dimensions, so we can still achieve smoothed estimates. And we use the person years as an offset in our model. So this is what hazard of out-migration looks like. And I'll draw you really to just one feature, which is especially present in Nagasaki residents. And there's a large spike in the hazard of out-migration in late teens, early 20s, which I think makes sense and is tracked with the literature that people are finishing school, they're getting married, they're taking their first jobs. So that's where we see a huge uptick in migration. Then we have hazards for in-migration to the catchment area. I think it's a little bit less interpretable, and this data set was a bit smaller, so I think there's also a bit more noise in the data here. But ultimately what we end up doing is sort of synthesizing those 2 pieces into a probability function, which can be done as a sort of recursive formula where we assume at the time origin, everyone is in the catchment area. And then we consider the 2 ways that in a small time increment delta, that you can be in the catchment area. So you can either be in the catchment area at the time just previous, and you don't move over the time duration, or the time step, or you were out of the catchment area and you move back in that time increment. So that's that formula there is sort of synthesizing that framework. So this is the final results that we'll be working with, and the big takeaways were that our LSS cohort members who were about 20 years or older when the cohort formed, or equivalently about 15 years or older at the time of bombing, are quite likely to remain in the catchment area throughout their lifetime, about 90% or greater. However, if you entered the cohort younger than that, there could be as high as a 40% probability that you will leave the catchment area and probably remain gone for forever. So in this upcoming analysis of cancer incidence, the last 10 years of incidence data is coming from individuals who were exposed at the youngest ages, and those individuals also have the highest migration rates. So this migration adjustment will be pretty imperative to this most recent update. This slide is all to say that when we do our LSS cancer incidence analysis, under some data conditions, we can show that in the data likelihood, we can just introduce those probabilities and it will give us a good enough approximation. And that is it for me. Several different conclusions and remarks, but actually the thing I want you to hear the most from my talk is that at RARF, we have several opportunities for student trainees and postdocs and international collaboration. So if anything sounds interesting or intriguing, I encourage you to reach out or chat. I will post a website in the Slack for you to check out. Thanks to my collaborators at RARF and of course the A-bomb survivors, their families, and their offspring for being such wonderful participants to our research.
All right, thank you, Hannah, and thank you to all of our speakers for this session.